speaker will be Chris Manning from Stanford. Thanks very much.
Okay, good morning everybody. So what I want to do today is give a fairly big picture talk without a lot of technical detail really about how work in neural networks for natural language understanding has been transformed over about the last 18 months. So that what we've been seeing is that there have actually been huge changes in natural language processing, that there were sort of methods that were being used in sort of 2014, 15, and I guess actually as recently as 2017, I gave a talk at the Simons Institute where I pictured this as sort of the default way people use neural networks for natural language processing. But here it is in 2019, and there's actually been a huge sea change in the kind of methods that people use. So I wanted to, give you a sort of a big picture sense of what and why things have been and how they've been changing, just so you've got sort of some idea of the big picture. I realize sort of basically the audience here isn't natural language processing people in any level of detail, so I'm trying to give an overview of that. And then towards the end, I want to say something about the idea of having knowledge and reasoning in neural networks and whether we can push neural networks closer to the sort of traditional notions of higher level of cognition, and talk a little bit about how we might try and do that in some work that I've done with students in the area of visual question answering. So that's sort of the program here of talking about language models and deep contextual word representations, and then moving on to whether we can have neural networks that reason. So when I got into neural networks about 2010, the idea that really motivated me was back when I was a young person in the 1980s, late 1980s, early 1990s, when neural networks were popular for the second time. From the point of view of human language, which was my background, it was seen that at that time the huge limitation of neural network models was that they didn't seem as if they could represent the kind of structure that human languages have. So human languages seem to have this kind of compositional structure, how you put together meaning. So you have something like very good, and you put that together as a unit which has a meaning of very good, but then you could modify that further with something like not and get not very good. And so what I was interested in doing was how could we build neural network models that use this kind of compositional structure of human languages to understand human languages. And with various people, especially Richard Socha, worked on that a lot. And we got some interesting, at the time good, results that seem to actually realize this vision. So here's an example of using these kind of tree-structured models for sentiment analysis. So the sentence is, there are slow and repetitive parts, but it has just enough spice to keep it interesting. This is a movie review. And the model is able to put a tree structure over the sentence and correctly work out that there are slow and repetitive parts, is saying negative stuff about the movie, has just enough spice to keep it interesting, is saying positive stuff about the movie, and the positive stuff wins. And so overall, this is a positive sentence. And that seems great. But in practice, this isn't the way that the neural network modeling world has gone. That instead, these kind of models, in some sense, haven't worked out great. And we could argue why they haven't worked out great. They're maybe too rigid in trying to sort of use this traditional linguistic structure, or it might partly also be because these models are sort of a computational disaster area compared to the kind of efficient models, neural network models that people have been able to scale up large scale. But, this doesn't seem to have actually been the big success. So what has been the big success? And so the big success has essentially been taking the idea of language models, a very sort of traditional, simple idea in prediction that has been used since the 70s for building statistical models of language, and making it bigger. So the idea of a language model is you've got something like the students open there, and you want to put a probability distribution over what's going to come next: books, laptops, exams, minds. And so we've got a word sequence, and then we're wanting to put a probability distribution over what word comes next. And if we add a stop probability into our distribution, then we can use that to give us a probability distribution over text. And this simple idea of language modeling has essentially been, for decades, the key part of most practical natural language understanding tasks. So things like speech recognition or spelling correction systems as decoding tasks make use of language model knowledge to try and work out what words are likely to be in a certain context. And natural language generation tasks like machine translation, summarization, story generation use language models everywhere to try and predict what kind of things that people are going to say next. So how do you build language models? So this is language models in the dark ages, which is approximately for most people until about 2012, let's say, to pick a number. So essentially what people did was took a big pile of text and just counted how often words come after other words, and you divide and you get conditional probabilities. Now that was both what everybody did till 2012, roughly, but it's sort of also a disaster area, right? That this is sort of classic curse of dimensionality because, huge number of words, one of those dictionaries about sort of 250,000 words. So if you're sort of wanting to condition on a couple of words of context and predict next words, you've got 250 million cubed parameters, and you're sort of very quickly into these sort of number of atoms in the universe kind of parameters that you'd like to know about. So people were able to build sort of good models, and so these are the sort of methods people use to do them. I mean, first of all, we made Markov models, which is saying, well, we can't model a lot of context before the word we're predicting, so let's only use the previous couple of words or something like that. The data was still really sparse because of our zillions of parameters, so we had to smooth our probability distributions. And sometimes we could use more context and sometimes less, and so people used ideas like back-off and mixture distributions to try and get things work. So at a first approximation, things could be gotten to work, right? And a lot of the early tools of natural language tools that many people will have been exposed to, whether it's things like spelling correction or machine translation on Google, these kind of technologies powered it in the early days. But it was then worked out that you could do a lot better by using distributed representations of words as word vectors. And really, Yoshua Bengio and colleagues pioneered this actually much earlier, around the turn of the millennium, actually, in the original paper. But it sort of then took about another decade before barely anybody actually picked up and started using this idea. But the idea now is we're going to have a real vector to represent each word, and then we're going to use those vectors to predict the next word. And that allowed us to solve two problems. Firstly, we could solve the curse of dimensionality in a certain sense, because these vectors for words could share components or directions of meaning, and so therefore we could generalize across words with similar meanings. But secondly, people then started looking at using recurrent neural networks to model language, and then we weren't restricted to only conditioning on a couple of words of context, and we could start conditioning on much longer contexts. And that's really, really useful for human languages. So here's a sentence from a novel: "The same stump which had impaled the car of many a guest in the past 30 years, and which he refused to have removed." So if you're simply building something like an n-gram language model and you're trying to predict what word comes next after he refused to have, whatever would come to mind, he refused to have an operation, he refused to have a dog, he refused to have a child, you're not going to think of stump, right? You're only going to think of stump sorry, you're not going to think of removed. You're not going to think of removed. You're only going to think of removed if you can see something like stump, which here is about sort of 15 words back. And so that's sort of powerful need for not using these kind of Markov model contexts. Okay, so essentially what's happened in the last couple of years is people have gone a lot further than before of saying, well, suppose we just take these kind of simple neural models whose job is to predict words, and we start scaling them up to much, much, much bigger models that do this job. And so we've sort of seen this progression where you could have models trained on 100 million words, models trained on 800 million words, models trained on 3 billion words, models trained on 40 billion words, and people have been getting to bigger and bigger models using vaster and vaster amounts of computational resources to train these models. But the end result has actually been quite amazing. So this is from the GPT-2 model that OpenAI did, which is working as a language model which predicts probabilities of next words. So you can then just sort of run it and say, generate some next words for me. So I'm going to give the first sentence of an article. A train carriage containing controlled nuclear materials was stolen in Cincinnati today. Its whereabouts are unknown. And then just say, use a language model to predict following words from that, and you repeat that over and over again, and so you get a continuation of a story. And we get the incident occurred on the downtown train line, which runs from Covington and Ashland stations. In an email to Ohio news outlets, the U.S. Department of Energy said it is working with the Federal Railroad Administration to find the thief. The theft of this nuclear material will have significant negative consequences on public and environmental health, our workforce, and the economy of our nation, said Tom Hicks, blah, 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 blah. So, this output is actually quite incredible. And it's incredible in two senses. I mean, one sense is a linguistic sense that basically, hey, this can just write English, that we're not getting something that's sort of full of grammatical errors and obviously broken. It's just coming out like sentences. But the other thing that's kind of incredible is that somehow, just by going to big scale, we've built a model that seems to know about the world. So in our prompt, we had a train carriage, nuclear materials, Cincinnati, which is all good, but, well, when we start to generate, well, it seems to know that Cincinnati is in Ohio. It seems to know that the Department of Energy is involved with nuclear materials, and it seems to know that the Federal Railroad Administration is a good thing to invoke when there's mention of a train carriage. And when you're stolen, you might want to have a thief, right? It seems to actually know a ton about the world, and that's kind of impressive and interesting. Yeah?
Some kind of post-processing on top of just extracting from the conditional probabilities?
Short answer is no, none at all. The slightly longer answer is it's using a particular way to generate this text, and it actually turns out that that is important. So the method that's being used here is that you're generating from a truncated probability distribution, so that using our neural network, it's got a probability distribution over all of the next words. And so the method that's used here, which is a successful good method, is say, let's truncate that distribution at the top 30 words and then renormalize and randomly choose from those 30 words. And that turns out, that sounds a little hokey, but that turns out to be a good method that works really well. Because if you always pick the most likely word, you tend to get very generic and boring text, because the most likely word tends to be a too common word. But if you actually use the whole distribution, there's still too much probability mass in the tail in aggregate, and once you head out into that tail, you tend to go downhill quickly. So this sort of truncated top-end distribution, or sometimes people use the top, p proportion of the probability distribution, has proven to be just a successful method to generate from.
Yeah. Just a quick. The reason I asked was because I was shocked that the grammar and the punctuation is fine.
The grammar language models learn grammar really well, right? I mean, even the older n-gram models that I was showing earlier, the count ones, really their grammar locally is pretty good already, because just a few words is actually pretty good for grammar. Normally where the n-gram models were no good at all is in sort of this longer text generation and understanding semantics. They'd produce things that was actually grammatically fine at the, if you just look at 5 or 6 words in a row, it's just if you read a whole sentence, it made no sense whatsoever. Was there another question there?
I was going to ask about grammar too. I don't know, I keep getting annoyed with TV commentators where the subject and predicate don't agree a number. Is the R in the title of that R unknown? Isn't the R incorrect? Because whereabouts isn't plural. Its whereabouts is a concept, and it should be singular there. Does that ever bother you, those things?
I'm not sure I quite agree. I think both tend to appear here for various reasons. But at any rate, we shouldn't blame that on the model, right? Because this part in italics was given to it as a prompt, and it's only generating from here. So if there's a problem with this part, it's the human beings who designed the prompts. It's not actually the models. In short, yes, wrong grammar can annoy me like any academic, but in truth, human beings aren't perfect themselves at doing agreement, and when there is intervening material or semantically complex cases, human beings themselves, when they make errors in agreement, there's actually been several psycholinguistic studies of that.
How much of this is in the training set?
So that's the obvious wonder, which is to say, look, maybe it's just ripping sentences out of its big training set, and it's not really generating anything interestingly different at all. That's actually not the case, and they what's that?
It was 40 billion.
Yeah, but they actually did do a study of that, and I'm slightly making up the numbers because I don't quite remember them, but it was something like the following. They said, okay, well, we'll define as copying if there's 6 words in a row that are coming from a sentence in the training data, and then what % of the text that we're producing is copied in the sense that it's 6 grams, 6 words in a row that from the training data. And the answer to that was really low. It was something like 3%. And so it really didn't seem that was the case. Yeah, obviously you have to pick enough words in a row because you can't kind of sort of really blame it for sort of saying US Energy Secretary, or even something like in an email to, well, maybe this one does get to 6 words, but you're clearly going to get multi-word units that are the same, and you can't but.
If I know that this is the way you're going to test me, then whenever I copy a longer sentence, I break every 6 words and put something.
Fair enough, but this was just a post hoc trying to get some sense of, was this just copying stuff? Okay, so the other, there's sort of stuff I haven't explained yet, which was actually, apart from the one on the right, all of these other models that I was talking about are actually a somewhat different kind of model called a transformer model, which has been super duper successful. And in fact, after GPT-2, there's sort of now being this increasing industry of a whole bunch of new transformer models that are at large scale and operating very well. And I'm not going to be able to sort of do all the details of how transformers work, but I just want to give a little bit of a sense of how things have changed and what things are doing. So there's this central idea that's been used in most work in empirical NLP, where the idea is that what we're going to do is represent the meaning of words by their contexts of use. And this is sort of an idea that has some tradition in linguistics. People often quote this quote of Firth, you shall know a word by the company it keeps. And it's also an idea that appears in philosophy. So in the later writings of Wittgenstein, he proposed a use theory of meaning, which is essentially arguing that the meaning of a word is the context in which you're allowed to use it. But for most of linguistics and philosophy, this is a pretty fringe idea, right? So by and large, linguistics and philosophy have worked with denotational models of semantics, which are in principle the same as the kind of denotational models of semantics people use for programming languages, if you've seen any of that kind of work. But under this model, which is sort of a very convenient model if what you have is a lot of text data that you can munge through, if we want to have meanings of banking or any other word, what we're saying is let's get a lot of text, find instances of the word banking, and then we're going to have all of this stuff around it and say that these contexts of use is the meaning of the word banking. And you can hope to start to get some ideas of sort of some of the things that go on in banking by finding sentences or having sentences that tell you things that are connected up with banking. And so what is now sort of the classic distributional model of word meaning, but classic means it's 6 years old, I guess, in the speed of neural networks, was this word-to-vec model that Mikolov and others pioneered. And so in the word-to-vec model, you're wanting to learn a meaning of a word type like into, and you're going to find contexts in which it appeared. And what you wanted to do is have a vector representation for each word, and therefore using that vector representation directly in this kind of softmax equation, you wanted to have the vector product of the dot product between two vectors, appropriately normalized, essentially give you the probability of two words occurring in context, where you're just sort of predicting each individual word independently, which we call a bag of words model. So this was the model that was proposed as a way of learning a vector representation of each word. And essentially, if you use this very simple model over a lot of text, you've got a representation for each word type. So banking, crises, into, turning, problems, that to a first approximation was semantically very good. It really did sort of show you notions of meaning similarity really well. I haven't got it running here, but when in my class, I just sort of run live one of these word-to-vec models, and people ask questions as to what words are similar to other words. Every year it freshly blows my mind just how well it works, such a simple model getting word meanings. And so it's this kind of simple model that has been the mainstay of a lot of the theoretical work that's been done on word meaning and deep learning. So that includes work like Sanjeev Arora's work, if some of you have seen that. But the problem with this is that although it's sort of useful to learn one meaning for words, and you can argue that words have, that the meaning that you learn for a word type is a superposition of all its different meanings, in practice, words have lots of different meanings in context. So if we sort of look down these word meanings for broke, I broke the, I say vase, vase in American English. I broke the vase. Dawn broke. He broke the silence. The news broke. The machine broke. I mean, all of these are so different, right? Like, I broke the vase. That's kind of the starting basics of it, right? Something gets turned into pieces, but when dawn breaks, nothing shatters. And when you break the silence, nothing shatters either. A machine broke. That's normally not broken in the sense of a vase. Sandy broke the world record, Sandy broke the law. There's something that sort of seems to connect these different senses of broke, but it's very hard to actually put your finger on what. And traditionally people have used an idea of saying a word has several senses. It's very hard to actually get a clear sense in your head as to which of these different usages you might want to clump together into a sense and which ones you wouldn't want to. It seems like there's this very nebulous meaning where words have very different meanings in contexts. And so the idea of the modern language models that are being used to represent word meanings, including these transformer models, is instead of coming up with one meaning for a word, what we want to come up with is a meaning for this token of the word broke here, and a different meaning for this token of the word broke here, and a different meaning for this token of the word broke here, where those meanings are again going to be represented as a high-dimensional real vector, but this time it's going to be for sort of in this one particular context, how should we represent its meaning? And so how can we do that? Well, the way people are doing that in transformer models is using this notion of attention, which is kind of in an abstract way connected to word2vec because you're sort of looking at the words surrounding you. But so what we've got is a word here, and we're going to mask it, and then we're going to say, let's use the context to see if we could reconstruct what that word is. So the sailor, the spinnaker. Okay, well, these words will have a word representation, which could be a word2vec word representation you start off with, but will be trained by the model as you train it. And then what we're going to do is do this attention operation. And so for the attention operation, you take a dot product between each of these vectors and calculate based on those dot products, a sort of a similarity measure. So these are our attention scores. And then you use those attention scores to get a probability weight over every context word, saying how much does each context word tell you about this word in the middle. So now, rather than just sort of having each word predicted independently, we're using all the words together with weightings to say which ones of them are important. And so that gives you an attention distribution. And then once you've got a probability attention distribution, you're then going to calculate a weighted average of all of these vectors to get an attention output. And I just copied this slide, it's attention distribution, but hopefully we might want to learn that actually spinnaker and sailor are the two most predictive words in this context. And so then once we have that attention output, what we can do is take our representation here and our attention output, combine them together by concatenating or something similar, and then put things through a softmax distribution again to predict a word, and we can hope to predict a likely word in that context. And so we're running this model over a lot of text, but we're going to use this model to predict representations of words in contexts. And so the transformer model is essentially built on this idea of attention distributions and just scales it up enormously to give an enormously big model of a kind that theoreticians would hate. So it seems like it's maybe not so good to have only one attention distribution because there are lots of ways in which words can be similar to and have relationships to and interact with other words in context. So why don't we have 12 different attention distributions at each position and combine them together? And so we do that. And well then, maybe it's too simple to just say that you do this attention thing with 12 heads one time to produce a new representation. So why don't we build a whole stack of these things where we repeat our multi-headed attention 12 times, producing a really deep neural network of the kind that people, this is sort of when NLP people have envy of vision people with their 100-layer networks, because most of NLP used to only use sort of 2, 3, 4-layer networks. So now we can have a big stack of attention distributions and have a deep network. And well, maybe as well as the multi-head attention, we could sort of stick everything through feed-forward layers at each stage as well to sort of learn parameters for a linear transform to do things. And we can put them all together and have this sort of very deep look around you many times and transform things, transform a network. And lo and behold, these models have just proven to be super, super successful at then doing prediction. And they can sort of predict all kinds of things. So here are just a couple of examples of this. So the Winograd Schema Challenge was an idea proposed by Hector Levesque, who's a sort of an old AI guy, and he said, well, what we need is a problem which isn't susceptible to sort of machine learning and simple statistics, something where people need to really reason and think. And so he turned to some old sentences from Terry Winograd's 1980s book, which he had used to justify needing knowledge and thinking, sort of common sense knowledge of the world. So if the sentence is, the city councilman refused the demonstrators a permit because they feared violence, who the they is the city councilman. And to a human being that makes sense, because if someone's refusing demonstrators a permit, presumably it's the people refusing the city councilman that feared the violence. But if we just change the word feared to advocated, the city councilman refused the demonstrators a permit because they advocated violence, well, then what makes sense to a human being is that they must be referring back to the demonstrators. And so Hector Levesque suggested sort of reusing these kind of sentences as a test of whether our systems actually have knowledge about the world to predict things. And he wasn't completely naive. If you read his paper, there's a whole section of it where he discusses, this won't be a good test if it's something that you can just solve by using Google. If you can type a few words into Google and look at the word counts and see that city councilmen feared violence occurs a lot more often than demonstrators feared violence, then maybe you could just do it in a cheap way with statistics. And he managed to convince himself that wasn't actually doable, and so that he still thought in the sort of mid-2010s that this was a good test of whether we had systems with common sense knowledge. And so that idea has been built on. People have made data sets of Winograd Schema Challenge, but it's just actually proven to be wrong, that these huge language models just learn all of this stuff. So this is looking at sort of scaling up a big language model. This is GPT-2 again, from 117 million parameters to 1.5 billion parameters, training it over more text and bigger models. This was about 63% was the best previous result that anyone had gotten in the Winograd Schema Challenge. Some of the models trying to do smarter things with sort of common sense knowledge and things like that. But simply just building bigger and bigger language models of this transformer size now gives by far the best results on these kind of Winograd Schema Challenges.
How much do humans do?
So
Average humans, not pigs.
I don't have a number in my head, but it has been measured. I think it's, humans are never perfect on things, but I think it's somewhere around 90-92, right? I mean, by design, these are meant to be things that are fairly obvious to humans, and I presume these ones seem pretty obvious to you, and quite a few of the others, if in some sense are even easier if they're sort of talking about objects and their interpretation. Yeah, humans do very well. Yeah.
This is supposed to be a counterexample to being able to do it without knowledge of the world, right?
Yes,
But
it failed.
how do we define knowledge of the world? Maybe you can just say, okay, so now the system does have knowledge of the world.
So that's a good question. And my time is fast running out, so I was gonna say a little bit more about how good these models are and what knowledge they contain, but it seems like I'm not going to have time to do that. So I'll go on to the end part that sort of seeks to answer your question. Let me sort of skip to here. I will give an answer to your question, and at least what I think. Yeah, so these big transformer language models have been super duper successful. Here's one last example of how super duper successful they've been. So there's been a lot of work by a whole bunch of groups on question answering, and the most used data set has been this squad data set that Percy Liang and students built at Stanford. And so the idea of this data set is that you have a passage. Super Bowl 50 was an American football game to determine the champion of the National Football League for the 2015 season. The American Football Conference champion, Denver Broncos, defeated the National Football Conference champion. And then you get a question of which team won Super Bowl 50, and the answer is the Denver Broncos. So these language models have been so successful that firstly, you can't be competitive on this test unless you use one of these big transformer language models. In particular, for the past year, the most successful one has been BERT, but that's starting to change now, actually. This is the leaderboard from February. But you could see at this point, BERT. Every model that was on the leaderboard was BERT with some doodads. And the second thing that you could notice is these models, at this point, were getting pretty much as good at human performance, and actually over the last 6 months have actually now beaten human performance, because humans aren't perfect doing things, but already here they're sort of very close to human performance. So that's amazing. But on the other hand, it's not the case that these models seem perfect. They actually still do very dumb things. So here's a dumb example. So this is talking about the Yuan dynasty, and it says in the middle here, in official Chinese histories, the Yuan dynasty bore the mandate of heaven, following the Song dynasty and preceding the Ming dynasty. And the question was, what dynasty came before the Yuan? And well, this sentence is a little bit complex, I guess, because there's this hard to understand bit here about bore the mandate of heaven. But, it's pretty obvious natural language understanding, right? The Yuan dynasty following the San dynasty and preceding the Ming dynasty. So what dynasty came before the Yuan should be the Song dynasty. 3 human beings were asked. 2 answered Song dynasty. The third one answered Mongol Empire, which you can sort of justify from the first sentence. I guess it depends on whether you count the Mongol Empire as a dynasty or not. But at least the temporal ordering of the human being's third answer is also right. But here we ask this supposedly all-wonderful BERT model, and it answers Ming dynasty, which seems pretty fundamental and basic, having no sort of understanding of what the sentence is actually saying. And this is a behavior that you notice still in all of the good question answering systems, even though they're so great, that it seems like a lot of the time the strategy you get out of them is basically they're really good at working out the semantic type of the right answer, and then they somewhat randomly choose an answer of the right semantic type that's near the centroid of words in the passage that are similar to the question words. And so in terms of what's left, so on the one hand, BERT and similar models have been this super powerful pre-training base for building natural language understanding systems. But nevertheless, they seem to have 2 problems. So one of them is that it seems like they're just the currently most powerful way of building a neural association machine, that they can kind of sort of learn all the statistics of what co-occurs with what in a much better way than anything that came before through these big attention machines. but they sort of look for what seems to be associated with what and choose something that's associated. They're not really sort of thinking through the meaning of a sentence. So this is sort of, what does thinking mean? And it seems like one thing that if you're actually thinking and reasoning, you should somehow be doing something more than just sort of measuring the strength of associations with everything. But the second thing is that although these models are very good for language tasks like this, that we're still building just these sort of one-off models for a particular task, that we're not actually sort of using a model that clearly has knowledge which can be deployed in different ways. And so in sort of going further ahead, it seems like what we'd like to do is have models that can flexibly redeploy knowledge. And so we'd like to be able to do things that are more in the nature of reasoning. So there was this influential paper from early in the current neural network era from Bottou, where he tried to make an argument for how you might be able to do reasoning in the context of neural networks. And well, traditionally reasoning has been the domain of logics and hand-built knowledge representations. But he suggested that maybe we could think about how we could use these learned distributed representations as a way of reasoning. And what he suggested is that maybe you could think about reasoning as algebraically manipulating previously acquired knowledge in order to answer a new question. So there are ways that you could do that that don't have to be traditional methods for logic, so that as soon as you've got some kind of algebraically rich inference system that connects together trainable learning systems, that you could think of being able to use those to do reasoning. And in particular, he suggested that central to reasoning is these composition rules, so that if you can put things together in different ways to address new tasks, that it's this sort of composability of having the flexibility to do things in different ways gives you something that's like human reasoning. And so an idea here is that, we have gone a long way in neural networks with coming up with designs for neural net architectures that give us the right kind of structure that allow us to do tasks well. So convolutions have been famously useful for vision. Attention has been the centerpiece of modern networks. Gating has been incredibly useful. Bottou's idea was essentially that we had a short-term memory, and when an input came in, we were getting two things out of the short-term memory. We were then composing them to get a new partial result, which we could feed back into our short-term memory and repeat. So essentially, this architecture was actually giving you a tree-like architecture, but over thoughts. So it essentially looks exactly like the tree-like architectures with which I began the talk, but using them over thoughts. So maybe exactly that isn't right, but it seems like what we'd like to be able to do is be able to sort of replace our sort of fairly unstructured correlation engines with some kind of neural network design that allows compositional and transparent multi-step reasoning, while having some of the good attributes of things like transformer models, that they're end-to-end differentiable and scalable to real-world problems. And so that's the kind of thing I've been interested in pursuing. And I'm kind of going to not have a lot of time left now to tell you the details of that, but I'll just give you a sort of a sense of the latest version of this work. So the most recent thing that we've been exploring is the idea of a neural state machine, which is having a differentiable graph-based model that's kind of like a traditional state machine for combining neural and symbolic approaches. So for solving problems, and we've been looking at this in the domain of visual question answering, we're first of all constructing an abstract semantic representation in the form of a graph or a state machine, and then we're going to be doing inference over that, which is sort of iterative computation over the state machine, so that we have an internal alphabet of embedded concepts. The states are then a distribution over those internal concepts. The edges are then transitions between concepts. And so when we then process with our neural state machine, we start with a probability distribution over the initial state, and each step we have a neural network calculating a state transition function, and so that will give us a distribution over a next set. So that if we have a picture, and then we're going to be asked a question about that picture, we're going to, from the picture, construct an abstracted scene graph as our neural state machine, where states correspond to objects and transitions correspond to relations. And then for the objects, they're going to have an attention distribution over different properties. And so what's going to go on here is then we can work in this space of abstract concepts and reasoning over them by walking through the state graph to be able to answer questions. So if we have a question like, what is the red fruit inside of the bowl to the right of the coffee maker? We translate that into an instruction sequence using an attention-based encoder-decoder. And then we can start to reason it through this state machine. So we start with a coffee maker, we go to the right of it, that's indeed a bowl. We can look inside it for something that's red, and we can answer that this is the apple. And so this kind of system has, by actually sort of pulling apart these representations, is giving us ways to do a better job at visual question answering. So there have been traditional ways of doing visual question answering, which have been sort of essentially convolutional neural networks for the vision part and neural sequence models for the language part, which have sort of worked sort of, but not great. And what I've been interested in showing is that by using these more explicit reasoning engines, so MAC was an earlier model that Drew Hudson developed working with me, and this neural state machine, that we're actually able to do much better jobs of reasoning and understanding our work. And so that's a direction that I'm hoping is very promising for the future, is how we can, first of all, seek tasks that require some multi-step compositional reasoning, and then try and build neural nets from them that, in some sense, do something more like thinking by having sort of iterative reasoning over more abstracted, disentangled concepts. Thank you.
Do we have time for maybe one or two questions while the next speaker is
I have one question.
Yeah.
Do you see any role for formal logical systems as helping out these problems?
So that is a good question. I mean, there's one answer one answer is, in certain places, I think, yes, there definitely is. I mean, way away from my talk, but an interesting place where actually there's work going on between formal logic and neural networks is one of my colleagues at Stanford, Michael Kochendorfer, works on aircraft systems like collision avoidance systems. And in the new generation of his systems, they're actually coding them as neural networks. And the reason they're coding them that way is for compactness, because they can have much more compact models that they can run on in less hardware on a plane. But that sounds sort of scary, because do you want your plane's collision avoidance controlled by a neural network? And so they've gotten, approval from the FAA to run these models because they're using formal, logical, formal logical theorem-proving methods to prove that this neural network does not run amok. So that's a good example of how the two are coming together. Relative to the traditional idea of using formal logical inference for something like natural language understanding, I mean, at this point I'm sort of skeptical that will work, that it's something that's been tried for decades, and language just proves to be sort of too squishy soft for things like how word meanings vary, like those examples I showed with broke. And so I think we have to be seeking something that, has multi-step inference like a logic, but has more softness than the traditional symbolic logic.
Let's thank the speaker again.